Okay, so here we are back again. I had a little technical difficulty. I thought I recorded the rest of the video, and then it only half recorded. So I'm making a second video, but you can see I've already filled out the um, information on the worksheet. Okay, so where I left you was I had asked you to calculate this projection, and I had asked you to draw the position vectors over here. Okay, so this will be quicker than usual, but maybe that's not a bad thing. Okay, so just to focus over here, all right, I found my dot vector of UV. So I had -1 times 4, which was -4. Then I had 4 times 3, which was 12. Okay, so that's going to give me as my dot product, it's going to give me 8. And in the denominator here, okay, I had to find the magnitude of vector v, and I had to square it. So my magnitude would be the square root of 25, but I've squared it, so I get 8 over 25. All right, then now that I have this fraction scalar that I'm going to multiply by vector v, then I can simply distribute this 8 over 25. Okay, so I'm going to distribute it across the vector 4, 3. So I'm going to end up with 32 over 25 as my x-coordinate and 24 over 25 as my y-coordinate. Now, I don't usually do this, but I have converted it to decimal form because I want to show you how it matches up with this picture over here. So let's look at this picture over here. Okay, so you can see my blue vectors are my two original vectors, all right? Vector u has its tail at the origin, its head at -1, 4. Vector v has its tail at the origin and its head at 3, 4, okay? So what I've drawn here is I've created a perpendicular from the head of vector u right down to vector v, okay? Because that is what's going to define my projection, okay? And then this highlighted pink section right here, that is actually my projection, okay? So it has a length, it's a kind of smaller version of vector v, and it has a direction, which is also the same as vector v, all right? But the reason that I wanted to put it in decimal form is because you can see here the head of this vector. Remember, I doubled these up. So this is going to be 1 and about a quarter, because 1 and half of a half. All right. So the x-coordinate here is about 1.25. I know it's going to be 1.28. So you can see how that's reflected in the picture. Okay. And then the y-coordinate of this vector head is, I mean, this is a little bit off, right? But it's getting close up to 1. So the exact value is 0.96. All right. So you can look at both the algebraic solution and at the, albeit not exact, picture representation, and you can see that they match up. So that's the idea here, to do it two ways and to show that the solutions are the same. Okay, so I've started to work through this, but you want to pause the video now. Try and work through these on your own. Be careful. In the first case, you are doing the projection of A onto B, and it's the full vector solution. Okay. In part B, you're doing only the scalar part of the solution. So you're also doing vector B onto vector A. So your type of formula is going to change, but also the setup of the formula is going to change. Okay, so just pause this and come back. Okay, so I'm just going to explain what I did here. So in part A, I found my dot product. Okay, 2 times 3, 4 times 3, 1 times 4. I added them together. I got my dot product as 22. The magnitude of B was square root of 34. So I square that. I get as my scalar multiple here, 22 over 34, which I can reduce. I divide both the top and the bottom by 2, okay? I get the reduced fraction of 11 over 17, and then I am multiplying that by vector b, which is 334. So you can see that you end up as an ordered triplet for your answer, because this is a vector solution. Okay, I'm going to have 33 over 17, 33 over 17, and finally 44 over 17 as my z component. Okay. Now over here, I had to find the dot product of b dot a, but remember it's commutative. So I had a dot b over here, b dot a over here. I didn't show my calculation, but you can do the calculation yourself and you'll find that they both come out as 22. And then my denominator here is the absolute value of a, because it's being projected onto a. So that's the square root of 21. I did do a decimal equivalent. You don't have to, but it just maybe makes the question, the solution, a bit more accessible. All right. So this is a similar question. So the hardest part here, so when you pause the video and work on this, the hardest part is reducing the fraction really when you get the scalar multiple. So please pause the video and then come back. Pretend I didn't write this stuff already. Okay, so you do the dot product, you end up with 14. I take my magnitude of v and I square it, I get 42. And then I have my vector v 145. So this is the trickiest bit a little bit. I mean, it's not hard math, but just to remember to do it, is that you can reduce the fraction of 14 over 42. It actually is both the top and the bottom can be divided by 14. I didn't notice right away. So you can reduce 14 over 42 to 1/3, and then you simply multiply vector v by 1/3, and I end up with 1/3, 4/3, and 5/3. Okay, and then we have one last question. This is the one I'm going to walk you through because this is an important thing, more of a thinking question. So notice here we're being asked to find or we're being asked to explore, I guess, the projection of A onto B. And the important thing here is that I am told that A and B are two non-zero vectors and their projection vector is the zero vector. Okay, and it says what conclusion can be drawn? Well, once I write out my formula, I can look at it and I know since the vectors are non-zero, I know that the magnitude of vector B cannot be zero. It's also in the denominator of the fraction. So you can never have a zero in the denominator of a fraction. It would be undefined. But so therefore that part's not zero. We know that the vector b is not the zero vector. So the only piece of the formula that would allow for us to get a zero vector as the solution would be if the dot product, the numerator of that fraction, is actually equal to zero. So that would only happen if the two vectors a and b were perpendicular. Okay, so that's the conclusion that can be drawn. All right, but you would have to show this to me. You might have already known when you read this, you might have suspected that this is what the conclusion would be, but I'm showing you a way to use the formula and your reasoning to actually map out why we would know this. Okay, that's it. All right, bye.